So now let's focus on the emission rate. The parameter that distinguishes the pollutants. Now, when we conduct air quality modeling, the only difference between pollutants, like say you want to measure the criteria pollutants like PM10. You know what PM10 is? PM 2.5, CO, sulfur dioxide, nitrogen dioxide, and so on. The only difference between these, right, is the emission rate. There's nothing else, because this model doesn't work with, doesn't change with the pollutant. The only difference, the only thing that you can add to the model that discriminates between the pollutant is the emission rate. So if the emission rate for carbon monoxide is 1 gram per second, it will give you one dispersion profile. If it's sulfur dioxide is also 1 gram per second, it will give you the same dispersion profile. It doesn't change. Maybe for nitrogen dioxide, there will be some slight difference because they try to model the change in nitrogen dioxide concentration because of atmospheric chemistry. But other than that, not that much. And usually we try to not model it because it will underestimate the value. We'll just use without the chemistry change, without the chemical changes in the atmosphere. So that's what it means by this statement here, the parameter that distinguishes the pollutants, that discriminates between the pollutants. If you have the same emission rate, the same results. The same emission rate value of two different pollutants would produce the same result. Oh yeah, see I mentioned it here. Except for nitrogen oxides, if we include ozone chemistry, but the way that they model it is quite simple too, because it just follows the exponential decrease. The further it is away, the more time it has to react in the atmosphere, the lower the concentration. That is basically how it works. Now, if the stack is yet to be constructed, like most of the time you want to run an EIA, Environmental Impact Assessment of an area. A company wants to build a factory with a stack, and it wants to assess the impact assessment, assess the environmental impact. We don't have any values from there because it hasn't been built yet, but we need to predict, right? So that's where we need to use the air quality modeling, like this one, so that we can guess on what is the potential impact based on the design given by the factory or by the company. So if the stack is yet to be constructed, it is estimated by, this emission rate is estimated by either mass balance. You know what mass balance is? So if there's 10 grams of particulate matter coming into a system, of course there's 10 grams going out. So we can guess from there, provided that there's no other leaks in the system. So for mass balance, we need to determine the fuel composition and likely exhaust gas products to obtain the mass flow rate. And mass flow rate is in the units of mass over time, like gram per second, kilogram per hour, ton per year, mass over time. If the stack has been constructed, we can go to the stack and then sample, but we need to sample, we need to obtain the emission rate, not the concentration. Remember, there's a difference between concentration and emission rate. Emission rate is mass over time. Concentration is mass over volume. Concentration doesn't, you cannot use concentration inside the model. You must use the mass rate or mass per time unit in the mass over time unit. So to do that, we use this technique called isokinetic sampling. Have you ever heard of isokinetic sampling? None? Iso means same, kinetic is movement, same movement, sampling. You put a probe into the stack, and then the problem with a probe in the stack is that it will impede the flow. It will obstruct the flow because there's something there. So you need to be able to sample without impeding the flow. So that's why they have to set it in such a way that anything that goes inside the probe that for you to sample would have the same velocity as outside. Hence the name isokinetic. Iso, so it's the same, right? So from there we can get the concentration, and then we also measure the velocity, and from the concentration and velocity we can measure the mass rate. Concentration is not useful, okay? You cannot go and sample concentration. Concentration, maybe you want to look at the characteristic so that it's not above a threshold set by the limit set by DOE, Department of Environment. But if you want to put it in the model, it has to be in the form of mass rate. Again, I stress that enough. You cannot just measure concentration. Most of the time when they do tests, they always measure concentration only. But it's not really useful. You need to get the velocity too. Okay, so I need to stop for a while. Okay, besides that, they have the blower specification. There's the ACFM, exit gas velocity. If you have the concentration, then you need to know. If you only have the concentration, then but you need to know the blower, because for every stack there is a blower that pushes it out. It doesn't just go up by itself. So sometimes the blower has a unit of ACFM, so it's actual cubic feet per meter, meter cube, actual cubic feet meter cube, right? Or at least the exit gas velocity. So this is a schematic for a stack. Of course, the stack height is from the base of the stack until the edge of the stack, the top of the stack. And then there's a stack diameter. Here you need to be careful. Sometimes the entire width of the stack is not the entire width of the exhaust, because the top of the stack could be round, but it's not entirely a hole. It could be a small hole in the middle of the stack. That is the actual exhaust. So sometimes you cannot use this stack diameter that they give to constitute the actual diameter of the exhaust. So you have to be sure whether maybe it's this one small hole here is the actual exhaust diameter instead of this entire thing. That usually, from my experience, that usually is a problem for power plants, because power plants have very large stacks. You've seen it before, right? You've seen the one beside Tesco. You saw it's very large, but it's not the entire thing that is a hole that releases gas. On top of it, there are 3 small holes, 3 small exhausts of different diameters, and the diameter that you want is those diameters, not the entire stack. Then the GIS. So here is just for you to put context on where for you to place the stack somewhere on Earth, you have to use GIS. So you need to know the coordinates of the stack. For example, here is a gas-fired power plant in Prai. One GIS software that you can use, which is free and popular, is Google Earth. And there's a way to link from the AirScreen model to Google Earth to show the results of your study onto Google Earth. If we have time, we can use that.